Movies on scientific topics are usually screened on the third Sunday of the month. Popular documentaries such as Cosmos by Carl Sagan, Ascent of Man by Jacob Bronowski, and Blue Planet by David Attenborough are shown. The program has shown a steady growth in its popularity. Universe in the Classroom. In this workshop, children and adults are introduced to observing the sky through naked eye, binoculars, and simple telescopes. The telescope that you see here is a high-quality optical telescope manufactured by Carl Zeiss. During the daytime, one can safely study the sunspots and spectrum of sunlight, beautiful rings of Saturn, satellites of Jupiter, and a host of other celestial objects can be viewed and studied at night. Workshops for content enrichment and practice of effective methodologies in teaching of science and mathematics are regularly conducted for school teachers. Summer programs for children, hands-on experiments, lectures by subject experts, visits to premier research institutes infuse interest and motivation to do science among children. SEED, or Science Education in Early Development, is a program for kids to learn science and mathematics through recreational activities involving toys and games. Base Camp is a 10-day experiential program for primary and high school children using science kits to make them feel science. Summer course is a 15-day thematic interdisciplinary course for high school children involving lectures, discussions, experiments, and field trips. From the web of life to the universe, a series of lectures introducing frontier areas of research to college students. Interactive sessions for high school students are held on Sundays. The students perform experiments, solve problems, and discuss concepts, all of which help in developing a lasting interest in doing science. REAP, or Research Education Advancement Program, is a 3-year rigorous course opportunities for REAP students to work with them and experience research environment. A similar program entitled Bio-REAP has begun for students of life sciences. The programs conducted over the weekends lay a strong foundation in the basics and develop problem-solving skills, which are essential for a researcher. students experience the joy of doing research. REAP students are pursuing PhD programs at various top universities in India and abroad, a clear indication of the impact of this program. In addition to the routine programs, the planetarium plays host to several reputed scientists from outside India to deliver popular and academic lectures. Please do visit the planetarium. Enjoy the cool environs of the Sky Theatre as the lights dim and you look at the sky dome, become one with the vast universe.
This is Science Watch, a review of recent developments in the fields of science and technology. What you are about to watch is a historic announcement being made at a press conference on February 11, 2016.
Ladies and gentlemen, we have detected gravitational waves. We did it.
That was David Reeds, Executive Director of Laser Interferometry Gravitational Wave Observatory, or LIGO. The announcement brought to an end the long wait of 100 years to detect gravitational waves by direct means. It took two huge detectors more than 1,000 scientists from 16 countries and a combined effort spread over 3 decades. A compelling reason for us to rejoice over this detection is a strong contribution from Indian scientists over the last 4 decades. The discovery team included 37 scientists from 9 Indian institutions, including the International Centre for Theoretical Sciences in Bangalore. Gravitational waves, popularly described as ripples in the fabric of space-time, are caused by the motion of massive objects such as black holes. Even neutron stars and pulsars create these waves. Here is the scenario concerning the first direct detection of gravitational waves on September 14, 2015. Two black holes in a binary system came closer and closer to one another as they revolved around a common center of mass. A fraction of their energy was continuously used up to produce gravitational waves, exactly as predicted by Einstein's theory. Finally, the two black holes merged into one. The ripples, with a characteristic signature produced by the merger, propagated outward in all directions in space. But barely interacting with anything, they could have gone undetected. But for an extremely sensitive detector, LIGO. Gravitational waves from the merger sweeping past the detector stretched and squeezed it alternately for about half a second. This caused a displacement far less than the diameter of the nucleus of an atom. Yet it was detected. Not by one, but by two detectors placed some 3,000 kilometers apart in Hanford and Livingston in the US. The signature of the gravitational waves submerged in an ocean of noise was picked up by a complex search method employed by computers. The last part of the observed signal, known as quasi-normal mode, was theoretically worked out as early as in 1970 by Professor C.V. Vishweshwara, the founder-director of this planetarium. The computers primarily search for the known signal pattern, including the quasi-normal modes, which lays hidden among enormous amount of unwanted disturbances, rendering the search more challenging than finding the proverbial needle in a haystack. In the process of detecting gravitational waves, scientists have shown that gravitational waves do exist, and the black hole and black hole mergers are also a reality. Until now, black hole and gravitational waves had a circumstantial existence only. Einstein's ideas about space, time, and gravitation have been subjected to rigorous tests. So far, it needs no modification. Since the first detection, two more black hole mergers have been observed. Each detection brings in its wake a library of information about the objects involved, their masses, their distances from us, and the mechanism that produce gravitational waves. As we detect more and more, we begin to understand a new language of the cosmos, and who knows, new phenomena governing it. For a long time, the only messengers in the cosmos were light. In recent times, neutrinos and cosmic rays have joined. Now that gravitational waves have joined, scientists can look forward to rather hear new and unheard of messages originating from the hitherto inaccessible regions of the universe. Surely, we are on the threshold of a new wave in astronomy and cosmology, a wave perhaps not even anticipated by Einstein himself. Einstein is once more riding the crest of a wave. Why not? After all, he created it, didn't he?
So, first of all, a warm evening to you all, and on behalf of Jawaharlal Nehru Planetarium and ICTS, I extend a very, very warm welcome to all of you. And going by the response, this has been an unprecedented one so far in Copy with Curiosity. Facebook being agog with lots of interest, and so we thank you for the support for this event. So as you all know, this Copy with Curiosity is a program that is held once a month, and we have very distinguished speakers speaking on a variety of topics covering various disciplines in science. And today we have Dr. Mahan Mj, who will be talking to us on the topic that you see shortly. And I request Dr. Gopakumar, the Director of ICTS, and request him to welcome on behalf of ICTS, introduce ICTS and its programs, and also to welcome the speaker. So, Dr. Gopakumar.
Thank you, Madhusudan. So welcome everyone. As was just said, it's very nice that there's such a big turnout for this event, and on Facebook and everything there was a great response. Thank you for your support. I will just give you a very quick overview of what ICTS is. ICTS is the International Center for Theoretical Sciences. We are located in North Bangalore, and this is a glimpse of the entrance to our campus. This is what the campus looks like from the point of view of the architects when they planned it. But this is a bit how it looks now with everything in place. So what we do we have our own research in various areas. I'll just mention. We have programs which are long period interactions of researchers in different areas where they come together at ICTS to focus, to collaborate on particular topics, as well as to teach younger researchers some of the most exciting developments in the topic. And finally, the third prong of our mandate is the outreach, of which events like this are a component. So we are modeled after very well-known institutes in the rest of the world, but we have significant innovations, and this is what makes it very unique in India and even internationally. Our research, we have a lot of young faculty. They do research in various areas in theoretical physics, mathematics, quantitative biology, and in the future, theoretical computer science and other directions as well. So we have a very active group that was involved in the gravitational waves and their analysis, about which you heard a little bit before. We have people working on theoretical aspects of gravity and black holes and so on, in statistical mechanics, condensed matter physics, biophysics, soft matter, and fluid dynamics, the study of turbulent phenomena, and as applied even to phenomena like the monsoon, and a broad mathematics group which is in the process of growing. Our programs, and this is just a snapshot of the different programs we've had, and these are different directions that we try to nucleate. Very often we organize programs in areas in which in India there aren't so many people working, and I've just chosen a few examples here, but the idea is to get people together to come up with new ideas on important research topics. And we've had, since its inception in 2007, ICTS has organized something like 125 programs and about 50 discussion meetings with a large number of participants, as you can see, with a good component from outside the country as well. And all the talks in these meetings have been archived and put on our YouTube channel. Maybe some of you have seen these channels with all the talks, including some of our signature Chandrasekhar lectures, Ramanujan, Turing, in physics, maths, biology, computer science, as well as other public lectures. Maybe some of you have come for some of the events in our main auditorium. We hold public lectures in ICTS as well. Let me advertise an event on 11th January. We will be having a public lecture by Kip Thorne. You might have heard of the person who was jointly awarded the Nobel Prize this year for gravitational wave discovery, an eminent theorist. He will be giving a lecture in memory of Professor Vishweshwara in our ICTS campus. So please come over there on the 11th. We'll of course circulate details on social media as well as otherwise. The programs that we've held span a vast set of areas ranging from the very big in cosmology to things in mathematics. In fact, Mahan and others are here as part of a program in geometry, where we've had things in biology, in computer science, and of course in things like condensed matter physics, and so on. So there's just a small sampling of the over 150 programs we've had. In terms of outreach, we've had various public lectures. As I said, they are all on YouTube. You can watch them if you missed them before. We've had Einstein lectures, in which a series in which we've had people going to various colleges. We were part of this Mathematics of Planet Earth initiative. So these are some of the things that ICTS does, and I hope I gave you a quick snapshot of this. And Copy with Curiosity, of course, is one of our flagship outreach events. Last year we had Professor David Gross, and that had one of the biggest turnouts in these. But we've been holding it with the planetarium mostly, and some other institutions in Bangalore as well. And I hope you will enjoy this Copy with Curiosity as well. So before I get Mahan to talk, let me just tell you, it's a pleasure to also introduce Mahan, because a particular pleasure to introduce Mahan, because I think it's fair to say that I've probably known Mahan longer than anyone here in this audience. We were together in school, and from a young age, and we went together to the IIT to study. He was studying maths, and then I was studying physics, but I mean, we've gone through many conversations on maths and physics and life in general through our college years. And afterwards, he went for his PhD to Berkeley, where he worked on three manifolds, and his thesis on hyperbolic geometry was a very important one, and he has been continuing with working on various aspects of geometry and dynamics. He's a very internationally well-known mathematician with very important results to his credit, including the existence of the so-called Cannon-Thurston maps in hyperbolic geometry. He's now on the management board of the ICTS, and involving himself more with ICTS as well. He was at the Vivekananda Belur University, the RKMVU, till a couple of years ago, when he moved to the Tata Institute of Fundamental Research in Mumbai, and where he's now a professor. So I think Mahan is very, as you will see, a very wonderful communicator, and I think he can get across the essentials of the subject, in this particular case about the shape and geometry of surfaces. So let me ask Mahan to bring the excitement of mathematics to you. But before that, maybe I'll ask our founding director, Spenter, to just come and give a small memento to Mahan as part of ICTS's token of appreciation. So over to you, Mahan.
Let me just... Okay. All right. Thanks, Rajesh. Thanks, Petra, for this somewhat overwhelmingly kind introduction. And thank you all for coming. The difficulty with a very kind introduction is that you're expected to live up to something. So, right. So I must apologize in advance. I mean, and also say that if I don't live up to these expectations, the fault is not mine. Okay. So now let's get on with business. So first, I'll try to. I'll be talking about surfaces and focusing on various aspects of it. So what are surfaces? And before we get to more formal stuff, we'll give a very low-level definition or understanding of surfaces by just pointing out to various things and saying that these are surfaces. Okay? So loosely, by dint of being members of the species that we are forced to live in 3 dimensions, and therefore when we see opaque objects around us, we are forced to see only the 2-dimensional surface, right? So I've used that word without defining it, and that's how really much of mathematics really comes up. I mean, you know what you want, what you mean, but to nail it down in terms of language that is formal and communicable, that takes a little bit of time. So let's see some surfaces before we try to understand what is the problem we are addressing and how we go about doing it. Okay, so if you look around you and just think that you're going to be looking at, well, surfaces of various 3-dimensional objects, there's quite a range, right? I mean, there's surfaces of chairs, clothes we wear, these curtains, walls, etc., etc. So it's quite a multitude here. So this is one of our standard shapes that we grew up with, namely a globe, and then there's a whole range of things. Pretty exotic ones, and then there's a whole range of these things, and it's not clear how we are going to, what one means by understanding what surfaces are. But so let's go back and see these pictures one more time, and there's just a sampler to indicate that if we are trying to organize and understand what all surfaces are, the problem is quite involved. Okay? And so we really have to have some kind of method of organizing this information. So now, what is the information that we have? I mean, firstly, we'll have to sort of narrow down, focus, and decide what is the information that we are trying to organize. Yeah? And loosely, as I said just now, in somewhat grandiose terms, it's all visual information, right? So by all visual information as processed by a human observer. Yeah? So, but how are we going to organize it? So therefore, some kind of dockets or folders in which we are going to put this and then pretend to ourselves that we understand all this. That's necessary, right? So there's this, I'm tempted to quote Poincaré. It was in French, but I'll paraphrase in English. It says that in mathematics what we do is we take things from a domain where we understand only in a nebulous fashion, and then take away the stuff that we don't understand at all, and put it under a carpet, and then we can successfully pretend to ourselves that we understand it. Okay? So it's what we'll do really is abstract out some part of the information, and then proceed to understand that. what is not understood will be conveniently shoved under this, this carpet, and after we proceed to understand one particular docket, we'll take out some stuff from under the carpet and then proceed to understand it. And that's how things proceed. Okay? So what we need is some kind of a formal structure. Yeah? All visual information is a very informal way of describing what surfaces are. So we need to understand what these things are in terms of stuff that we can actually put on paper and communicate to other people. So what are surfaces? Yeah? And we'll have to have a definition, a clear notion, which we can communicate to other people. And the answer, again, this is not entirely a completely precise answer, but it's a first level abstraction of when we said that we are looking at opaque objects as human beings and we are looking at the surface of that, what really are we doing? And we are really looking at the two-dimensional surface of the object that we are interested in. So what are surfaces? So basically, if you are looking at say this podium or a chair or the wall, we disregard the fact that this is actually the surface of a three-dimensional object, and by this mental process of abstraction, we take out just the top surface, which is locally two-dimensional, which means that we are not looking at it any longer as three-dimensional human beings, but looking at it as a creature living off that surface would treat it. So for instance, so suppose, for the timing, suppose this one was an ant crawling on the surface of this blackboard, it would regard this green board. This green board would look two-dimensional from its vantage point. That's not so far removed from what we, as human beings, used to think of. A few hundred years back, we used to think of the Earth as flat. So what happened was that the local structure of the Earth was what we used to regard it as. So something that is locally two-dimensional. So our vantage point is not that far removed from an ant's perspective. So all these things are really surfaces. Yeah. So that's what we are trying to study, locally two-dimensional, which means if you don't think of this whole thing, don't look at the Earth from space, but look at it from your myopic viewpoint, then you're going to regard it as flat, as something two-dimensional. Yeah? So that's an example of what we are looking at, and it's almost forced on us by the kind of organs of vision that we have, namely, yeah. So these are the objects that we are going to study, and then I said that we are trying to understand them. Yeah? So what does trying to understand them mean? And basically what we want to say is that given two locally two-dimensional objects, we would like to say whether they are true, whether they are equivalent, or whether they are really different, whether they are truly different. Yeah? So we need a further understanding of what we mean to understand these guys. Yeah? So what does classifying these two-dimensional objects mean? When we say we understand, we typically mean that if there's this vast range of objects, we've devised a convenient method of putting them into dockets. And so let me elaborate on this a little more. So what does classification mean? So let's try to, when we say that we are going to understand these objects, let me try to get at what really we are trying to do. So first thing is that we really want an exhaustive list of these dockets. Yeah? So basically, so this list is a collection, a list of abstractions in a certain sense, which we'll be making more precise as we go on. And the same object must not occur in various places. So for example, suppose we are in a position to distinguish chairs from tables. So two chairs would be the same object. Yeah? So a chair would be distinguishable from a table. And so two different kinds of chairs would not occur in our list. That's what I mean by this exhaustive list with no redundant elements. But it should be exhaustive in the sense that all the objects that we are trying to understand must belong to this list. So, second is, okay, so we have this list, which you should not think of as concrete objects, but as dockets. Yeah? So when one person says to another person who understands English, when we say this is a chair, that chair actually stands for, it's a placeholder for a whole collection of objects, all of which have certain characteristics similar to the chair. Okay? So that's this exhaustive list. And so the word chair is an abstraction of the material chair. I mean, that's what I'm trying to get at. But this list is exhaustive in the sense that we should have a list of all surfaces, and if somebody gives me an object and I say, okay, yeah, this is a surface, I should be in a position to say that it does occur in this list. Not only should I be in a position to say it occurs in this list, I should also be able to point out to you which object in this list it precisely is. Yeah? So the first thing is an exhaustive list. The second thing that we need is to say, given two surfaces, they are the same, which means that they belong to this particular docket, which is given by this exhaustive list. Okay, so essentially, first a list, second a method of saying, a method which will terminate in finite time. It's also called an algorithm of saying which precise object in this list it is. So this is formally so since this is ICTS has this mandate of having theoretical computer science, mathematics, physics as science without boundaries. I mean, so the basic notion, a certain basic notion that comes up in theoretical computer science is the notion of an algorithm. This has a precise notion. For the time being, since we are talking only in reasonably loose terms, just think of a method which will terminate, which will have some finitely many steps, which will take as input an object which one says is a surface, and it's going to output for you which precise one on that list it is. Yeah? So this is really what understanding meaning classification is all about. Yeah? Okay, so now we've understood what we mean by classifying, what level of understanding we are going to have at the end of this process. But what are the objects? And I said that the objects that we are going to study are locally two-dimensional objects. That's still too imprecise. We need to have a more formal way of describing local two-dimensionality of an object. And that's where we are going now. So let's try to look at some more locally two-dimensional objects and then decide what our formal, precise notion of a locally two-dimensional object will be like. So let's go back to this picture of the globe. And if you look at, it's been cut out by latitudes and longitudes. If you look at a tiny piece of this globe here, say this rectangle here, and you cut it out and put it on paper, it looks just like a piece of graph paper. Right? Does everybody see that? Yeah? So, I mean, just look at this globe, take a small part of that, cut it out mentally, and place it on paper, and you have something that looks like something that has x coordinates and y coordinates. Yeah? So something that has x coordinates and y coordinates, yeah, is what we are calling two-dimensional. Why? Because there's one for x and one for y. That's it. So that stuff. So let's look at some more examples. I mean, this is actually something from a computer simulation. So this is supposed to be a picture of a rabbit. So it's been divided up into pixels So if you look at a small part of the surface of the rabbit, cut out a chart, I mean, then what happens is that this little piece of the surface of the rabbit and the little piece of the surface of the globe, they look actually exactly the same. Yeah? So if you cut out a small piece of the globe, you cut out a small piece of the rabbit, which has conveniently been cut out here, they don't look too different. Yeah? So you can put x, basically what does it mean? You have local x coordinates going, and it's, very fortuitously, the x direction is not horizontal, and the y direction is not exactly vertical, but that's okay. Yeah? All that we need is, if you look locally and you specify two pieces of data, namely the x coordinate and the y coordinate, you would have decided exactly where the point on that surface looks like. Yeah? So this is really what we are really now getting towards a precise notion of what it means for something to be locally two-dimensional. It means that every point you take a point on your surface, take a small little patch around it, and you need two pieces of data. You can put x coordinates and y coordinates on it, and these two pieces of data are going to determine for you precisely where that point lies. Okay, so now with that motivation, this is something that if you're not familiar with the terminology, that's okay, but because I've already described what it means. So a surface, and it's a locally two-dimensional object. And so mathematicians have this somewhat disconcerting habit of, once you've done something for 2, maybe for 1, well, there's nothing particularly special about 1 and 2 except for the anthropomorphic accident that we are three-dimensional creatures. So you generalize and say, okay, so look at n-dimensional, where n could be 10 to the power 23. So that's why this 2 here is just a way of democratizing this set of objects. So locally, something is two-dimensional, has a special name, it's called a surface. If it's locally n-dimensional, it's got a name, it's called an n-dimensional manifold. So 2 is not special. A surface is also called a two-dimensional manifold. It just means locally everything is two-dimensional. Yeah? Okay, so what does locally two-dimensional mean? It means that, well, if you don't know this particular word, homeomorphic 2, doesn't matter. All that it means is that around every point, you can put x coordinates and y coordinates. Yeah? That's all that it means. And homeomorphic means that the axes, the x coordinates and the y coordinates, need not be horizontal and vertical. They could be bent, yeah? As in the picture of the rabbit. So we've seen one example of what a surface is, of what a two-dimensional manifold is, namely the surface of a globe. Are there any other examples? Are there any other examples that you see in day-to-day life? And yeah, any surface that you can think of which you think of as something that's essentially distinct from the sphere? A donut, fantastic, excellent. Yeah. Okay. So this is the surface of a donut, and so now if you look at a point on the donut and you cut out a small piece of it, it looks like a rectangle. You look at that. If you look at that little piece of a rectangle and look at a piece of a rectangle on the surface of the Earth or on the surface of the rabbit, you will not be able to distinguish between them, right? So locally, all these guys are the same as having x coordinates and y coordinates, being locally two-dimensional. So the donut is another example. Are there others? So now let's try to. So there are two problems, as I said at the beginning. One is we are going to try for an exhaustive list, and second, we are going to have a method of saying when two of these objects are the same. Yeah. So now we've got a notion of what kind of objects we are trying to look at. But we also need to make precise when two of these objects are same. Yeah? So let's say, so this is a particular word. It just means that they are same in the domain of discourse. Yeah? So we say that two surfaces, S1 and S2, are same, homeomorphic. It's a particular technical term. It just means that they are same in the context that we are talking about. If you can go from one to the other without tearing or gluing, yeah? Which means that there should be a bijective map. So every point on this first surface has to go to the second surface, and it has to come back by the inverse of this map. So that's setting up a one-to-one correspondence between the points, which respects the local structure of being two-dimensional, such that local structure being two-dimensional is preserved by what are called, so tearing and gluing are not allowed. It just means that this map is continuous. So that's again a word. What does it mean? The intuitive idea is that the first surface can be deformed to the second surface without tearing and without gluing. Okay, so let's give some illustrations of what I mean here. So you have this, well, supposed to be a dumbbell with 3 bells. Okay, so you start off with this gadget, and then you start deforming it. So these necks become thicker and thicker, and this more rotund part of this object, that becomes narrower and narrower, and then there's a particular kind of flow that is happening. So this gadget here, yeah, it's actually flowing, yeah. So it's the places which are more sharply curved, there the curvature is shrinking, and the places where there is this kind of thin neck, those parts are becoming fatter and fatter, yeah. So what's happening is that this asymmetric part of this dumbbell, right, the asymmetry of the dumbbell, yeah, is gradually vanishing, and it's becoming, tapering. These things are becoming less narrow, and now it's becoming smoother and smoother, and then you finally have almost a round sphere. Yeah. And let me just throw something at you, because this is not really this is in 2 dimensions. Yeah. Perhaps the finest theorem in this area over the last several decades, devised by a Russian mathematician, it was proven by a Russian mathematician called Grisha Perelman. What he did was he devised a method of making precise how this curvature flows to something that's nice and round, starting from any shape. Yeah? And this led to the resolution of what was the holy grail of this field. This field has a name, it's called topology. And this led to a resolution of something called Poincare conjecture, which was made in 1905. And essentially, this is a toy example of what really went into the solution of that problem. Okay, so it's continuous deformation, such that what happens, such that I've used some words, such that parts of it which are more curved become less curved, and parts of it which are less curved become more curved. Yeah? Anyway, so this is the process, and if you can deform one to the other, you say that those 2 objects are the same. Yeah? In technical terms, they are homeomorphic. So now we again, just to step back from this, we wanted a list. We got 2 members of that list, namely the surface of a sphere and the surface of a donut, and now we understand what it means for 2 of these objects to be the same. Another example, you have a wrinkled lemon, and then you allow this to flow, and it becomes a nice, round, smooth lemon at the end of it. All right. So now that we've understood the problem, we have to solve it. Yeah? So what's the problem? We'll have to get an exhaustive list, and one will have to say which object in this category, which object in that list it is. Yeah? So this is a problem now. So I'll give you 3 examples. Yeah? And I'll ask you at the end of the day whether these three objects are the same or different, where same means one should be deformable to the other without tearing, without gluing. So this is, well, this is what it is. You have another one and you have a third one. So this is actually something like so think of this like a teapot with three handles, but don't try to drink tea out of it. So it's a round sphere with three handles attached to it. Yeah. So now let's look at these three objects and try to decide whether these three are deformable. I mean, are they resembling the same object, where the same means that they are deformable to each other? Yeah. So are they the same, which is different, etc., etc. So I'd like to invite answers from the audience. This is different. Excellent. So this is different from the first two. Okay, good. Anybody else? So venture an answer. Yeah, I mean, at worst, they are the same objects. Yes? They all three are the same? Or two are the same, the third is different? Somebody is saying all three are the same. Okay. Yes? Yes, somebody here? All three are the same? Yeah? Yes, our youngest scientist here says that all three are the same. Excellent. Very good. Yeah? 1 and 3 are the same. All right. So 1 and 3 are the same, but 2 is different. Yeah? Okay, so now let's see. So the bets seem to be conveniently hedged, but we can't do politics here. We have to, so democracy has no, place. So let's see. So you said that all three are the same? No, you did. Why do you say that all three are the same? Yeah, can you wave your hands a little bit and say why you can deform one to the other? Let's focus on 2 at a time. Yeah, this one and this one. So 1 and 2, right? Yeah.
Well, we can kind of move two discs, okay, 2 donuts around one and make it like.
Which one do you want to move? Do you want to move this one, or this one?
Okay, I'll move the bottom one.
You want to move this one? Yes.
Yeah, to the counterclockwise.
Counterclockwise.
Without tearing.
Without tearing.
Just stretching the material.
Just stretching this part.
Yeah.
Yes.
So if I move it completely towards the other end.
Yeah. So then, if you move it a little bit, then this will become. There'll be this hole, and this will be very skewed, but it will be towards the end, towards the bottom of this.
Yes.
And then if you move it further and reflect it, you're going to get this.
Yes.
So that's the correct answer. And really, this is how we reason. Yeah, I mean, it's, So, I mean, one can start writing down equations for this motion. Yeah. Firstly, one will have to write down an equation for this gadget. One will have to write down an equation for this gadget. But the simple, intuitive content of it, chances are that's going to be destroyed. So yes, let's go with this. Yeah, let's go with this argument. You catch hold of this ear and pull it, drag it along till it comes to the bottom. Okay, but that's good. So that explains that 1 and 2 are the same. Yeah. What about 3? So somebody said that the first and third are the same. Yes. Why would you say that? You can sit and answer. Yeah. Yeah.
If we keep applying forces from all the 3 sides, the center part would become a ball, as shown in the third picture.
So let's not apply force. I mean, we can be non-violent, right? So we can just try to blow this part up a little bit, right?
Yes.
Okay.
Yes. I think that's what I thought.
Yeah. Okay. Go ahead. Yeah, and then do what? And finally, what will happen is that the central part is going to be swollen.
Yes, yes.
Yeah, and it's going to give you this, and there are going to be these 3 handles attached. That's also a correct answer. So essentially, just think that you have a little, this is made of some flexible material like the surface of a balloon, and there's this part here which you catch hold of and blow, and assume that this stuff is made of fairly rigid rubber with less flexibility, and if you blow this part up, you're going to get this stuff, right? And then from this point of view, it's not easy to see directly that this guy and the second guy are equal, but if you've deformed this to the first and the first is deformed to the second, then we had this axiom when we started learning geometry in class 6, things which are equal to the same thing are equal to one another. So we use that same notion, and then all these three things are the same, right? Okay. So these three gadgets that we've drawn pictures of are really the same, and you've already discovered for yourself what it means to prove that two things are the same. Yeah? Basically, you want to give some kind of reasoning so that you can deform one to the other, continuously without tearing. So now let's come to the main theorem. This is a theorem which I shall not prove. Essentially says that if you have a closed, so I'm giving some technical terms here, which I'll go back to this picture and illustrate for you. If you have any closed, this term has not yet made an appearance. Any closed orientable surface is the same as, read this word homeomorphic to as the same as, a sphere with n handles for some integer, positive integer or 0. Yeah? So let's go back and see what it is. So this is really the most convenient thing. You have this, this is the surface of a sphere if you removed all the handles, and then you're attaching, basically think of a teapot with n handles. N can range from, if it was 1, it will be a sphere with a single handle, that looks like a donut. If you had 2 of them, looks like a pretzel, and then so on. Yeah? So essentially this object here is a prototype of what all objects that we are trying to study are. Yeah? We have now let's go back, and this is really how stuff is done. When you try to classify, you see that there is some wild phenomenon somewhere, and therefore we put in adjectives to eliminate that wild phenomenon. And this word closed is a method of doing precisely that. It essentially says that at every point it looks two-dimensional, but there is no boundary. There is no part of it where you fall off. Yeah? So it's not like what some of our ancients thought, that if you go on the surface of the earth far enough, you're going to fall off it. That's not going to happen. Yeah? So every part of the surface is a part of something that's locally two-dimensional. You go on that surface long enough, you're going to come back to where you started from. Yeah? So that's the kind of object that we are studying. That's what the word closed here means. This word orientable, this requires a little more clarification, which I'll go on to. But for the time being, let's forget this word. So any closed surface which you see in 3 dimensions. Yeah? So any closed surface which you see. So let's take this word orientable to mean that's something that you see around you. Now, for the time being, and I'll give a more precise notion, is going to be the same as homeomorphic to a sphere. Here, this one has 3 handles. You could have 1, 2, n for any positive or non-negative integer. If you had 0, you'd have just the sphere. All right. So now let's get to this word orientable. What does orientable mean? Yeah? It basically means that it has well-defined sides. Yeah? There's an outside and there's an inside. Yeah? So if you have something that's closed in 3-dimensional space, you can think intuitively that there's going to be something that's inside and there's going to be outside. This is going to be an outside. Well, it's a fact which we shall not prove or in any sense, is that if you have a closed surface, and it is in 3 dimensions, you can actually prove this statement. There is going to be an inside, there is going to be an outside. In other words, it is going to be orientable, which is why you don't really think that there is any need for introducing this word orientable when you're looking at surfaces in 3 dimensions. But if you're looking only locally, then then there is an example of a non-closed surface which can be seen in 3 dimensions, which is not orientable. And here's the example. I'm sure somebody has seen this kind of stuff before. Yes? Yeah? Yeah. So, yes? Anybody? Yeah, so this is called a Mobius strip. That's the name. So essentially what you do, I mean, you can play this game, take a thin little piece of strip of paper, cut it out, take one end, and give a pi twist, and then glue it to the original side again, and then you're going to get this. I suspect this is a painting by Escher, but I'm not very sure. Don't quote me on that. Is it? Yeah. So why has he drawn these ants there? Yeah, so these are ants. Yeah. I mean, these are actually pretty decent paintings of ants. I mean, yeah, I certainly wouldn't be able to draw such a faithful replica of an ant. Anyway, so why has he drawn these ants here? What is he trying to illustrate? There is only one side. So there's this outside and an inside, which we talked about just some time back. So that, how are you going to locally determine what's an outside, what's an inside? Yeah? So basically what you do is you fix a point on your surface and then poke a perpendicular out of it, yeah, into this ambient space. You have 2 directions, right? If you have a plane, you can have a perpendicular going to my right, your left, or you can have a perpendicular going in the other direction. So assume that your surface is like this, yeah? So what's happening here is that if you look at, say, a little patch of this Mobius band, this surface here, then the middle legs, those are poking up. That's something like a normal pointing out of the surface. So at your starting point, you make a choice. It does not matter which choice you make of a normal pointing out of the surface. Yeah? So then you start following the ant around and look at where the middle legs go. And once you've come here, now you finally, if this ant goes all the way around, it's going to finally end up at the picture of this ant, and you can see that its middle legs are pointing downwards. If it goes below, it's going to be just underneath the first ant, and the perpendicular is going to point exactly in the opposite direction. Right? So, which means what? You started off at a point, you made a choice of one direction, called it outside, and then you went around the loop, around the surface, and you came back to your original position. Remember that this gadget, the Mobius strip, is really a 2-dimensional object that we are looking at. Yeah? So so at a point, so it's drawn for thickness again because of human limitations, but really you should imagine this as something that's infinitely thin. It's just a 2-dimensional gadget. So there is this point and there is no second point on the other side. If you thicken it, there are 2 points, yeah? But if it's infinitely thin, those 2 points are the same. So when this ant comes back to where it started from in terms of a point on the surface, what has changed? The normal direction pointing out of the surface has changed. Yeah? So which means if you call locally one direction as outside and one direction as inside, this is a completely ad hoc definition on this particular surface, because when you come back, the outside has gone to the inside has gone to the outside. Yeah? So for a gadget like the Mobius band, sides are not well defined. Okay? All right. So this is an example of something that is non-orientable. Now let's try to manufacture, put these 2 adjectives together. Yeah? Closed and non-orientable. I said that we will not be able to prove formally in the space of this lecture that there don't exist closed non-orientable surfaces around in 3-dimensional space, but we'll try to convince you that that is indeed the case. So what's going on here is essentially you're taking two of these Mobius bands and then you're gluing them together. So what's happening is that this is an annulus. You take an annulus, yeah? So an annulus is just a cylinder, yeah? And if you glue them end to end, you're going to get a donut, correct? Just take a long pipe and glue the ends of the pipe together, yeah? You're going to get a donut. The surface of a donut, also called a torus, yeah? What if you flip one end and then try to glue? That's exactly what's going on here. This stuff is going around in this direction, and at the other end, which was pointing and it was going in the other direction, we are forcibly twisting it in the wrong direction, and then we are trying to glue the other end. So basically, if you have this stuff going around like this, if you come here, it's going to go around the circle in the other direction. But if you try to glue these two things together, so basically what we are doing is what we did with the Mobius band, we flipped one edge by a pi rotation and glued it. What we are doing here is the same thing, but for a circle. So take instead of an edge cross a line, yeah, for a strip, we are doing the same thing for an annulus here, yeah. So this gadget has a name. Oops. This gadget has a name. It's called Klein. It's called the Klein bottle, but anyway, that's just a name. It's the circle cross eye with the circle glued back to itself by a flip. Yeah? And you see that if you try to glue, then this is a part where this thin part of the annulus has to intersect the fat part of the annulus. So if you try to do this stuff in 3 dimensions, you're forced to intersect yourself. Yeah? This is not whimsy, this is not an accident, it's a fact of life. We can't have, I mean, so people have made an industry of manufacturing Klein bottles that you can't drink out of. And yeah, so there are these exotic things that are available, I think, on eBay or Amazon, etc., etc. So this is an example of another Klein bottle, but again, you can see here that it has to intersect itself. Yeah? All right. So this is really the reason that when we made the statement about what the classification is about, we talked about closed orientable surfaces. Closed non-orientable surfaces you don't see around for a very good reason. They don't exist in 3-dimensional space. Okay. So now let's try to drag out. I had promised that there's some stuff that we have forgotten, some structure of the surface that we have forgotten. We've allowed ourselves to bend and distort shapes at random. Yeah. But what really are we distorting? We said that this curvature of an object, etc., we were decreasing curvature, increasing curvature. That's really something that we were disregarding from the discussion so far. But now let's drag that little bit which we have comfortably shoved under the carpet out and try to understand what is the extra structure that we were trying to forget. So these shapes that we were talking about, which we were able to successfully classify as a sphere with n handles, but now try to focus on it locally and longer, more carefully. And what we realize is that the surface of a rabbit and the surface of a sphere are locally the same in terms of just having x coordinates and y coordinates, but the shape is not exactly the same. And so they are same in terms of deformations. That's the field that it defines, called topology, but not geometrically, where geometry is now determined by what is called curvature. So we'll now try to get at this is really the last part of the talk, and really you should think of what is geometry. Geometry is something that's more precise than this continuous deformation. So geometry has an older history than topology, and it's called geometry done on rubber sheets, yeah? So more flexible stuff. So now let's go back to stuff which is more rigid, namely, and try to understand what this curvature is about. And so can I borrow your, thanks. So this is going to be the most involved picture here. So this object here is this dodecahedron here. right? So this is a gadget which has, thank you. So, so there are these solids that we know of. These have a name and they have a rich and varied history. Basically what these gadgets here have, they have a common property. Each vertex here, each corner here has the same number of faces hitting it, same number of edges hitting it. Every face has the same number of edges. It's as regular as you can think of. Yeah? And there really are, well, this gadget here, this is something that's a little more involved than this one. So this has 12 faces, this has 20. So this is a tetrahedron. This is a dodecahedron, this is an icosahedron, this is a cube, and so on. Yeah? So these 5 objects are all the solid objects which satisfy this property that every point is on the same number of edges, same number of faces, every face has the same number of edges. Now, question, if you imagine these made of some flexible material and you pump in air, all of them are going to be nice round spheres, right? You try to blow these up, assume that these edges are flexible, you're going to get nice round spheres. So topologically, all these gadgets denote for you, I mean, they are the same from our previous fluffy point of view. Yeah? So they are all the same as the sphere with 0 handles. Are they different? So how are they different? But you can see that they are different, right? I mean, they don't look the same. They don't look exactly the same. So how are we going to distinguish? And essentially, the information is really contained at the vertices. So let me just have a show of hands to see. See, this point here and the point here. Which point do you think is sharper? Yes? I mean, so the tip of the tetrahedron or the tip of the dodecahedron? Which is sharper? Tetrahedron. So how are we going to make that precise? So what does sharper mean? Yeah? Yes? Solid angle. Good. Excellent. And so what about the solid angle? What will say that the solid angle, if the solid angle is such and such, we'll say it's sharper. If the solid angle is smaller, we'll say it is sharper. Excellent. All right. So let's now try to formalize exactly that statement as a definition. So the surfaces are all the same as they are topologically the same as the sphere. Curvature at the vertices are different. Yeah. And so the solid angle, what you were talking about, is really what measures. I mean, from this solid angle, you can extract exactly. Well, let's see. Well, a slight modification of the solid angle is going to give us the notion of curvature at a point. Yeah. So how are we going to measure the curvature? And what we do is really, I mean, so what we are trying to measure is the deviation. So what is something that's not curved at all? What? The plane. Yeah. So the plane is what we call flat. Yeah. So there's no curvature. It's completely flat. Yeah. So what we are really trying to measure here is the deviation from flatness. Yeah? So instead of, and now the curvature, the notion of solid angle is really a three-dimensional object. Yeah? What we'd like is a notion that is more two-dimensional. We are trying to study surfaces, so two-dimensional gadgets. Yeah? So how are we going to do that? And what's the angle around the vertex in the flat plane? So if it's something that's flat, what would be the angle around a vertex? 2 pi, 360 degrees. So here's a simple way of measuring the defect. You just look at the sum of the angles around a vertex, take the difference from 2 pi, and that by a fiat, we define that to be the curvature concentrated at that vertex. Okay? So the difference between 2 pi and the sum of the angles around that vertex is what we call the curvature concentrated at that vertex. All right? Now let's do a computation. Okay. So let's go back to this picture, the model that Drupad had, and let's try to compute the angles around a vertex. Yeah. So how many faces does this have? This has 12 faces. That's excellent. So here's a way of drawing this stuff on a plane, on the board. So let's see. This should be visible. So there's a way of drawing this. So you draw a pentagon, then draw 5 edges coming out of these 5 vertices, and then you complete these 2 pentagons. Yeah? And then again from here, you poke out single edges and then join them all up by, well, I'll join them up by a circle. You're supposed to draw it by straight lines. Okay? So essentially what you've done is you've taken this pentagon and then you've projected it onto a plane where you can see all the edges and all the faces except the rear face. Yeah? All right. What did we want to do? We wanted to compute the angle defect. We wanted to compute, so this is not something that we use frequently. We don't use the dodecahedron frequently in day-to-day life. So what's the curvature around each vertex? So firstly, we'll have to compute the internal angle of a pentagon. Yeah? So what's the external angle of any polygon, any convex polygon? That's 2 pi, right? So that means each external angle would be 2 pi by 5. So the internal angle would be pi minus 2 pi by 5. Is that correct? Yeah. So that's 5. Yeah, that's 3 pi by 5. So each internal angle is 3 pi by 5. Yeah? 3 into 180 degrees divided by 5. So therefore, what's the curvature at each vertex? By this angle defect formula, take 2 pi, subtract how many vertices are there around a vertex? There are 3 of them. So there's 3 pi by 5 here, 3 pi by 5 here, 3 pi by 5 here. So that's 3 plus 3 plus 3, that's 9 pi by 5. The defect from 2 pi, that's equal to pi by 5. How many vertices are there? Well, let's count, and that's why I drew this picture. So there's 1, 2, 3, 4, 5, and then you go around at the next layer, there are 5. At the third level, there are 5, so there are 4 layers of 5 vertices. Yes? So there are 20 vertices, exactly. So the total angle defect, therefore, is equal to 20 times pi by 5, which is equal to 4 times pi. Yeah? Okay? All right? Now let's go back to our pictures. And now this is the one picture. I will not do the exercise of the icosahedron. That's going to be something that you can do at home. Yeah, it's going to take too long. But now let's do it for a cube. So each angle at a vertex is how much? Pi by 2. How many of them are there? 3 pi by 2. What's the angle defect? 2 pi minus 3 pi by 2, that's pi by 2. How many vertices are there? 8. So pi by 2 multiplied by 8 is 4 pi, right? So for the cube also, the sum of the angle defects, if you sum, you're getting 4 pi. Yeah? Let's do it for the tetrahedron. So what's the angle of it? So each face is an equilateral triangle. Angles are pi by 3. Total angle around the vertex is pi by 3 plus pi by 3 plus pi by 3. That's pi. Angle defect, 2 pi minus pi. That's pi. How many vertices are there? 4. What's the total angle defect? 4 times pi. Some black magic going on, or? Well, no. So this is a theorem. And so what you do is you look at all these angle defects. If you take take something that's topologically a sphere, which means you assume it's made of some flexible material, blow it up and becomes a sphere, and now you divide it into cells. Then you look at the sum of all these angle defects. The curvature is concentrated at these vertices. You're always going to get 4 times pi. It does not stop there. This was by Gauss. This is a theorem by Gauss, and you get something that's even stronger. This is by Gauss and his student, I think, Bonnet. Essentially, if you take the sphere with n handles, yeah, and do the same exercise. So, for example, you could think of just say a rim of a sofa. Yeah. So basically, that's going to be a polyhedral description of the donut. Yeah. For the donut, you're going to get 0 as the sum of all these relations. Yeah? So this is the polyhedral Gauss-Bonnet theorem. You take a sphere, you take n handles on it, and you look at a cellulation of that, which means you decompose that into polygons. And then you sum all the curvatures concentrated at vertices. You're going to get 2 pi times 2 minus 2n, or minus 2 pi times 2n minus 2. So when the number of handles n is 0, it's minus 2 pi times minus 2, which is 4 pi, which is what we've already obtained. Okay, so I'll stop there. Thank you. Yeah, I'm sorry for going over time. Yeah.
Thanks a lot, Mahan, for having brought topology and geometry to everyone. So, as you know, the format of the Copy with Curiosity is that we keep a lot of time for people to ask questions and have a discussion. So, please ask your questions. Please keep it short and precise. Yeah, please ask. There'll be someone with a mic. Please wait for the mic to come to you.
And if it's all clear, we can all go home.
Yeah.
A business case of like what we had discussed, topology.
Yeah.
I mean, an engineering or a technology case where this is, rather than being a puzzle.
Oh, I see. What you're saying is this actually, is this just something that we do for a pastime we play with, or whether it has actual serious applications? Yeah. The answer to that is we do it for a pastime. It also has serious applications. Okay, so let's see. What would be a... So, for example, this is something that's happening nowadays, and Rajesh is definitely much better equipped to talk about this. So, suppose you have current being passed through a material. Yes? Oh, I think there's somebody else who's... Yeah. So, and if you have some part of that material which is not quite the same material, it's some defect inside that material. Yeah? Pardon me? No. I'm talking about defects in material, say in conductors. Yeah? So you don't want to smash your stuff and see that there is some defect inside. You want to pass current, and so somehow or the other, independent of the shape of what the material is, that defect inside is going to be measurable by stuff that you just do on the surface of the conducting material. Yeah. Which means that this, so basically, so what am I trying to say? So assume that you have some kind of a solid conductor, yeah? And from inside you've removed some of the metal, yeah? So that's going to, I'm giving a very, very crude example. I'm not an expert in this area. So, but if you try, you will be able to, without cutting that material and seeing that defect inside, by making some measurements on the surface, you will be able to detect that it's not made of the same homogeneous material, but that there is some defect inside. So this is... So, yeah, so you can guess that this is going to be useful, right? What has... So essentially this having a defect inside of some particular shape is something that's detectable from not going inside the surface, but just from surface measurements. Yeah? So the topology of the... So basically what is it saying? It's saying that the topology of a solid conductor and the topology of a solid conductor with a hole removed from it are not the same.
Yeah, good evening.
Yeah.
Here, behind the pillar.
Behind the pillar.
Yeah, the pillar also, I think, has to take a
right.
anatomy.
Yeah, so this is an example. So this pillar is basically, if you take a, so this is quite a, so if you take a string and you keep winding round and round this pillar, yeah? So and you come back to where you started from, you will not be able to haul that string to yourself, right? Without cutting through this pillar, right?
That was not my question.
Yeah, so if you, but on the other hand, oh, that was your question?
No, that was not my question. But we
have enough time to answer. On the other hand, if this pillar was not there and you've gone around this room several times with a string attached, yeah, and you come back to where you started from and you start hauling the string back, you're going to be able to contact the string. Which means what? That the global topology of this room with the pillar and without the pillar are not the same. Yeah. So, for example, I mean, one question that we would like to know is that, okay, so this world we live in is locally three-dimensional. What is its global topology? Yeah. So, we can't do it using strings. I mean, well, using ropes. But we can think of, say, the next best thing, sending rays of light out and hope that it, I mean, we can put it into some kind of formalism, basically by saying that it goes around, and then whether after you close this loop, whether you can pull it back to yourself or not. Yeah. I'm definitely overstretching to domains where I have absolutely no idea what I'm talking about. Yeah.
Sir, good evening. When it comes to the topology of a human anatomy and when it comes to artificial intelligence being applied for robotics, of how we are going to animate.
So the topology is not going to be. So, for example, I mean, there are certainly more. So, for example, I mean, terrorism is a menace today, right? So you would like to be able to say that a particular human face and another human face, they are the same or different. Yes? So there, I mean, just take the human head, yeah? And, well, it looks like a sphere, right? So topologically, you won't be able to distinguish very much. On the other hand, the shapes of our various features on our face, they are quite distinct, yeah? So geometry does come into play. What you're doing is you're representing your face as a two-dimensional gadget, and this brings in certain sophisticated aspects of geometry, yeah, which can distinguish. I mean, you can take two human faces in terms of you're going to take two-dimensional representations, which means you're going to take pictures. And then you're going to say whether these two pictures are of a person who poses a threat or does not pose a threat. Yeah? So there are actually quantitative methods of looking at this curvature, representing it in two dimensions, and then making these comparisons. Yeah? There's a famous algebraic geometer. Well, once upon a time algebraic geometer. Now he does this kind of stuff. This is a field of what is called pattern recognition. And the person, one mathematician who has done a fair bit in order to make these structures fairly formal is David Mumford. Yeah? So there is, in 2002, for some of the mathematicians and others in the audience, so in 2002 he gave this International Mathematical Congress address where he did talk about certain aspects of geometry, basically called quasi-conformal structures, which can be used to distinguish, I mean, which can be used in pattern recognition fairly well. So that's how, in the process, I have given a more authentic answer to your question. So it is used very, yeah, to actually use, yeah. Yes, please.
Thanks for the wonderful lecture. I just had a bit of difficulty with the homeomorphism between, say, a cube and a sphere.
Yeah.
So what about the discontinuity at the edges?
Excellent. Okay. So what it means, so for example, so if you start, take say the skeleton of a square, yeah? Now you put in your rubber balloon there and you blow it, and then it's going to be constrained by these edges, right? And so assume that it fills it up, right? It goes right till the corner. Okay? Now, what you can do is just remove these constraints. I mean, remove this frame from it, and then you allow it to blow further. It's going to become nice and round. What's going on is that, so you are feeling uncomfortable about these corners, which were sharp, yeah? what happens is that this map is not something for which, so for example, I mean, let's go one dimension less and make it very visible. So think of just, I mean, a straight line which is bent at a point, which is broken at a point. So it goes straight and then bends sharply. Yeah? That and just the straight line or some smooth curve. What happens at that point is that the derivative, that changes. So for example, y equal to mod x is not differentiable. Yeah? Y equal to x is. But those are still continuous. Mod x, y equal to, I mean, x going to mod x is a continuous function. The graph of that is something that you can get from the graph of y equal to x by continuous deformation.
Like, I mean, squaring the circle.
No, yeah, well, no. So don't get into such exotic, yeah, I mean, those are much more rarefied domains. Yeah. So it's all that's happening is that you will be able to say at what speed you are changing. So, for example, if you are moving down and then at one point suddenly your velocity has moved in the opposite direction. So, if you will compute acceleration, I mean that's going to be infinite at a certain point of time. But it's a second order change. As a first order, there is no change.
Yeah. Hi. Good evening. I just wanted to add a couple of points to. I think one person there asked about the applications of topology. Topology and geometry.
Yeah.
So actually, I'm working with AI and RPA, so robotic process automation, and there are a lot of geometry-based algorithms that we use in machine learning, and you can say neural networks that involve deep learning and TensorFlow. So with particular, if you talk about the shapes that are involved in, you can say regular geometry, such as, so all of these, we can implement them while developing algorithms using machine learning. And a lot of these, I've come across a lot of algorithms that Google's Alphabet uses. You can say even for Google Maps, or Uber is using for developing its deep learning, you can say the algorithm as such.
Yeah.
So
the only thing
computer science is.
Can you please ask a sharp question?
No, I just wanted to tell that a lot of these formulae are being used in computer science. So that's it. Yeah.
Okay, before 1 second, we'll come back to questions here. There are people upstairs also in the overflow room. So we'll take, they've sent a few questions. We'll take some from there, and then we'll come back to questions here. So one interesting question is the rabbit a sphere or a sphere with one handle? Since a rabbit is just a tube, which is the gut, so shouldn't it be a donut and not a sphere?
Okay. So I think I had made my jailbreak statement right at the beginning. So we are going to be looking at only the surface of the rabbit, not the. So once we see something that's two-dimensional, we do not exercise, we refuse to exercise our imagination to see that there is a gut inside. So which means that we are just going to think of this as the surface of the rabbit. We are looking at two-dimensional objects, so just the surface of the rabbit. And imagine that rabbit is made up of some I mean, so you had that picture that was there on the slides. So if you imagine, if you will, a balloon which has the shape of a rabbit, and if you remove all the strings that keep its ears and tails constrained, then you're going to get back to a nice round balloon, which is the abstraction of the sphere.
Sort of sellotape the mouth.
Right.
On the other end. So there's a couple of questions from here. Can you please repeat the name of the 3D? It says three-dimensional infinite shape, which you said is available in eBay and Amazon. I think he or she means the two-dimensional and non-orientable
Right. So this is the Klein bottle, Klein. Yeah. So just Google Klein bottle, Klein bottle. I mean, these are all the pictures that were there were stolen shamelessly from the internet, and you're probably going to find these pictures there also. So yeah, I mean, and there's a particular company, at least in the United States, which definitely manufactures these things as mementos or curios.
So hopefully, if there's a surge in the purchase of these, they will donate 10% to ICTS. So anyhow, we are not particularly endorsing any company here. The next question is the number of handles the only feature we see to differentiate between orientable surfaces?
Yeah, so for closed orientable surfaces, that's what this theorem says. That's a complete invariant, which means that for n equal to 0, 1, 2, 3, 4, you have this infinite list, and you take any closed surface, it's got to be a sphere with some n handles. N could be 10,000, n could be many, but it's got to be one of them. So that's a complete invariant. That's what this really means.
One more question before we come back here. Are there any major unsolved problems / contradictions in topology? And within brackets, assumptions which undermine the field?
Oh boy. So, no, I mean, well, let's put it this way, that the kind of things that could actually undermine it happen to be in. So I think we are cushioned with there are other fields of mathematics in between topology and something more foundational. And what we are really looking at here, I mean, this is going to take us away from this field. Basically, what is the tool that when one is talking about something that's going to undermine a field, it basically means that you should be in a position to prove a statement and its negation. Yeah? So we could in principle prove that the sum of the angle defects on a sphere is 4 pi for some cellulation, and then somebody manufactures a new cellulation and says that out of this for this cellulation the sum of the angle defects is not 4 pi. Yeah? I've claimed that there is this age-respected theorem of Gauss and Gauss-Bonnet, which says that the angle defect of any cellulation is 4 pi. Yeah? So if somebody proves, without making mistakes, that the sum of the angle defects of some particular cellulation of the sphere is not 4 pi, then one would have arrived at a fundamental contradiction. The domain where one has to hunt for such contradictions is not either geometry nor topology. I mean, one has to unravel, in a certain sense, what is the logical structure that underlies these deductions. The field, that's a field called mathematical logic. And essentially what is believed is that the axioms, what is there underlying all this is the set of axioms that underlie what our naivest notion of a continuum is. What is the real line? Yeah? And there are certain names I'm going to throw at you right now. I mean, they are called piano axioms. And the deepest, perhaps the single deepest mathematical logic theorem of the 20th century, proved by Kurt Gödel, essentially says that if you take any sufficiently sophisticated mathematical system, which means it builds on sufficiently sophisticated set of axioms, you are not going to be able to disprove it. Yeah? So basically, these piano axioms, which give rise to arithmetic, which give rise to the real line, etc., etc., you are not going to be able to prove that you are not going to arrive at a contradiction. Yeah? So, but we go on with the belief that these axioms are consistent because What can be done is you can increase your set of axioms and look at this logical system from a slightly larger perspective. I'm being very loose here. And essentially say that the first set of axioms that you started off with are actually consistent. So if something is provably consistent from a larger standpoint, I just hope there are no logicians in the audience, then you will not be able to come down. You throw away this larger point of view, bring yourself back to the narrower point of view. Then from this narrower point of view, you will not be able to prove the consistency of the set of axioms that you started off with. Yeah? So I don't think we are in any serious, real danger of our field being endangered by proving a proposition and its negation. Yeah.
But maybe you can address the first part about major unsolved
yes.
topology
Sorry. Yeah.
also.
Okay.
I mean,
That's,
in addition.
Yeah.
Like you mentioned, the Poincare conjecture, which was proved by Perelman. Is there any something of a similar sort of a stature or close?
So I think, so the correct thing to say here is that probably no other conjecture apart from the Poincare conjecture. And essentially, so the statement that we had made here was this classification of two-dimensional objects in terms of genus. Yeah, so that's that number n, number of handles, is also, it's got a name. It's called the genus of the two-dimensional surface. The next step of that program is to classify locally three-dimensional objects. So two-dimensional objects were studied and classified at the end of the 19th century, essentially. Yeah. Classifying locally three-dimensional objects is something that has happened in this century. So it took more than 100 years. And the greatest input to that was this theorem of Perelman's that I talked about. It's also a theorem that if you look at locally four-dimensional objects, then they are not classifiable in a very formal sense. No computer is going to be able to generate an algorithm, a method by which it's going to drop this classification theorem. So it's a theorem that there does not exist such a theorem in 4 dimensions. Okay? So in dimensions 2, it's reasonably easy. One can give a 1-hour talk and explain to you the content. 3 dimensions, it's much harder. It looks like, it looks pretty wild, but still there's a classification theorem. It took a lot of mathematicians working for a long time, and it's finally been resolved. Dimension 4 and higher cannot be resolved as a theorem. So coming back to the actual question, what are directions where one goes? And essentially, so let's put it this way. So we have looked really at just 2 aspects of surfaces here, closed surfaces here. The first was from a purely topological point of view. The second was in terms of curvature. Yeah? And we had this Gauss-Bonnet theorem, which says that the total amount of curvature is some topological invariant, 2 pi times 2 minus 2g. What one can do is one can try to put, geometry is not just curvature. There's a whole range of structures. So we have looked at only 2 things, right? So one where you're allowed to deform things continuously, and then say 2 things are the same if they can be deformed to each other. The second thing is that point-wise the curvatures are the same. There's a whole slew of structures in between. Yeah? And so basically a geometry is really born out of what are the symmetries you put on the surface. So what is it that allows you to say that these 2 surface with X kind of geometric clothing and surface with Y kind of geometric clothing are the same. Yeah? So the symmetries of the space, in the first case it was just continuous deformations. In the second case it was curvature preserving transformations. The entire idea of geometry is really contained in that word same, which means different things in different contexts. Okay? So yeah, it's sort of ironic that the word same means different things in different contexts. But Anyway, so you can make that notion of same subtler or finer, and then you're going to come up with various notions of new geometric structures which arise very naturally in different parts of mathematics. So the study of surfaces is by no means a closed chapter. In fact, the conference that we are going to have next week at ICTS, for which we have been building up, well, not a conference, it's some discussion meeting, which means that various mathematicians are going to come together and discuss various things. And we had a 3-week preparatory workshop which led up to this. It's about some of these structures in between. Yeah, I mean, they're very precise, well-defined notions of equivalences. And so we are studying it. So it's a topic of current interest in the most literal sense possible.
Sir,
I'm sorry I can't go into that in more user-friendly terms because it's going to make me very technical. Yeah.
So we can come back to questions here in this audience for a while. So the mic,
Sir,
the person with mic
yeah,
there.
for any solution of the sphere, we said that total angle defect is 4 pi.
Right.
Does this have anything to do with the fact that total solid angle around a point is 4 pi?
No.
No.
So for example, I mean, imagine it's really, I mean, what I'm really trying to say is that you should forget for the time being that we as human beings are three-dimensional creatures. Yeah, so try to think of the surface intrinsically in terms of its two-dimensional surface. Yeah, it's a pure two-dimensional theorem. It has nothing to do with, so you can imagine surfaces which do not sit. You can imagine spheres with particular curvatures which are not embeddable in three-dimensional space, which means solid angle. See, actually, okay, so let me give my little spiel. Solid angle is useless.
Okay.
Okay? It's in this particular context, yeah? So when you're trying to study a two-dimensional invariant, you're taking an intrinsic, I'm sorry, I mean, for sounding doctrinaire, but for locally studying that, yeah, three-dimensional space in which it is embedded is a red herring. So useless is not the right, it's a red herring. I mean, it gives you a certain idea that you might proceed there, but it does not really help. You have to come back to the local.
Like the Klein bottle that you
That's
mentioned,
right.
you
Yeah.
have a similar
Yeah.
thing, but there's no notion of. But there was a question there with the mic. No, the person with
maybe
behind.
I can
the person
elaborate
behind, I think, was asking first.
Yeah,
please.
I am a little nervous asking this question because what I'm imagining is a little difficult to explain.
Go ahead.
Say I take a cube made out of cloth,
and
I stitch the seams in a way that it becomes a sphere.
Yeah.
So if I draw along the seam lines, there's a certain way I will draw the lines on a sphere.
I didn't quite get that last statement.
So I have a cube.
So you have your cube. You've got your stitched cube now.
Yeah, and I blow it up so it becomes like a sphere.
Yes.
So the lines are drawn in a certain way. So if I cut along those lines, I'll be able to put it back as a cube.
Okay.
So now if I take a sphere, can I randomly draw on it and make some pattern that can be cut and put back as a solid shape with, say, flat surfaces? Or are there any rules that...
So I'm not sure I completely understand your question. So for example, I mean, you saw this picture of a dodecahedron, for instance, right? So that's basically you can take a sphere and you decompose. So for example, I think this is the best illustration. So think of this as a map of the globe. Look at a globe, right? So the countries are randomly determined, right? I mean, there's some political flux which keeps changing these. So that's some kind of cellulation or some kind of some kind of decomposition of the surface of the Earth. Yeah. You can make those edges straight. For example, most of the states in the United States have polygonal boundaries, except for the parts that are on the coast. States that are in India do not. Right? So you can have, I mean, and you can see that the map of the United States got a cellulation, right? In terms of finite number of edges. States of India don't. So that part of it it's not a restriction at all. Okay. I'm not sure I'm answering what question you have in mind, but it's...
So say if the United States of America covered the entire globe, if it covered the entire sphere.
Metaphorically.
Metaphorically.
It's a very dangerous statement. Yeah. Yeah.
And if I cut along the lines of the states,
yeah,
and when I stitch them back together, is it possible to have a non-spherical space with
maybe,
faceted edges?
Okay. So stitching together means, so for example, let's if I okay, so this is going to be another interpretation of your question. So for example, you take the surface of a cube, yeah, and you cut it into polygonal shapes, yes, and now you reassemble the polygons, not necessarily gluing them back where they were, yes. Can you get, say, the surface of a donut? Would that be a reasonable interpretation of your question?
Yes.
The answer is yes.
Okay.
You can always do that.
And there's no rule for what are the angles?
No, if you keep the geometry fixed, geometry of the shapes fixed, then it's difficult. Yeah. So, for example, I mean, you take a cube and you punch a hole right through the cube. Yeah. And then you have the surface of this punched cube is the surface of a donut, right? So imagine you take a small square to take a hollow. So basically, you want to construct a hollow square or a hollow cube out of a solid cube. Yes? If you're allowed to stretch, then you can certainly do it.
Thank you so much.
Hello, sir.
Yeah. Oh, there was somebody else.
There was someone there.
Hello.
Before.
Yeah. So as I understand, you have said that topology is breaking down of a three-dimensional object and studying breaking down of a three-dimensional object.
The word
topology.
Yeah. Topology. Yes.
Is breaking down of a three-dimensional object and studying its surface.
No.
Right?
No, that's not quite right. So topology is study of all geometric shapes up to an equivalence. That notion of equivalence is homeomorphism or what I described as continuous deformation, right? It need not be two-dimensional objects. It could be three-dimensional objects. So this theorem of Perelman is a theorem in topology. So it's not just about, so this is an example of what we study in topology. This is not all of topology.
Okay, but it's mainly to do with surfaces which are...
No, it's not mainly to do with surfaces. Surfaces are part of topology. Topology has surfaces as one aspect of it. One important aspect of it. Not main. I mean, there are zillions of other things which we study in topology which are just as important as the study of surfaces. This is how the study of, where the study of topology really starts. It's where it started historically.
So is there anything like a study of single dimension? Well,
one-dimensional?
Yes.
Oops. So, unfortunately, in one dimension, the study becomes quite boring. So, what happens is that if you look at the same problem, what is the collection of closed one-dimensional manifolds? Yeah? There's one extra adjective which I forgot, connected, which means they're not in several pieces. The only thing that you get is a circle. Yeah? So, there is only one object in that category, which means up. So, topologically, one dimensions is quite boring. Well, you have to put in extra structure to make it interesting.
Hello, sir.
Yeah.
Sir, I have a doubt. Is this limited to shapes around us only? Or
no, that's what it's not. It's not. That's what I was trying to say. That if you look at locally 15-dimensional shapes.
Because I'm asking.
Well, actually, that's So this is right. So I think there are some. So
because,
locally,
I have another question.
Yeah, locally things which are 6-dimensional make a lot of sense to at least two members in the audience.
So not only dimensions, sir. Yes, sir, I agree. Not only dimensions. If you see the shapes of galaxies, shapes of collection of stars, or shape of Saturn's disk. Many things are there in universe. So what about them? Are we not considering topology of them?
Certainly. So the thing is, when we are looking at shapes of galaxies, etc., See, okay, so I'll have to make another statement. Yeah. The point is, we take these natural objects and then we abstract out some properties, put it on paper, and then study the shapes, right? So what are we doing finally in the study of surfaces? We are looking at this abstraction and we are studying it, right? We are studying the model, right? Finally, at the end of the day, if you tell me that this model does not replicate something in the real world, I, as a mathematician, will be forced to say so much the worse for the real world. Okay?
That's correct.
So the thing is, it depends really on how well you're modeling. So, of course, galaxies, but that's not what we are studying here. It's a certain level after you have abstracted out. I mean, all fields are doing that. I mean, you abstract out a certain piece of information because you can't, I can't catch hold of a galaxy and show it to you, right? So I'll have to write down equations for it, model it in a certain way.
So you are telling
that abstraction
their equivalence and their equations will be changed, and it will be complex like that. You are telling?
Pardon me?
Are they complex to real world?
No, it depends. So it depends on what you are abstracting out, right? It's finally forget. I mean, these fields are really defined by a certain limitation of our brains.
Yeah. So are there any universal laws for this, like topology, because surface, like my skin is also surface, and the same as the
right.
Saturn.
So let's take exactly that example. So if you start studying the surface of your skin, if you study it at this very loose mathematical level, it can be modeled by a continuous object. Start looking at it closely. It's composed of cells. It's no longer a continuous object in that
same
sense.
As the galaxies, no? Same as Saturn's disk, craters of moon, many things. Same as surface of.
If you any object, take any object, you can study it at different scales or in terms of different models, and each model is going to give rise to a different theory. Some of that is going to be what you're going to be calling very, very randomly mathematics.
Thank you, sir.
This is the most coarse way of describing. Then there are finer and finer ways of describing. I think topology is the most, at some level, the very essential, very essential part of this. 1 second, there is a question.
Yes. Use the mic. Yeah.
This is just a question about the Klein bottle. Firstly, I wanted to ask, how do you spell it? Was it C-L-I-M-B or C-L-E-I-N?
K-L-E-I-N.
Klein. Oh, okay. Second thing is, I don't understand. So suppose the ant was that thing, would it come back to the same place? Because the thing that you showed there, I couldn't. The ant was walking there.
Shall we get that picture again? So these were two different things that we were seeing. An ant on the Klein bottle. So this is where you're referring to this one. The next one. Yeah.
So basically, there was an ant on the one of those rings.
Yeah.
Then that part.
And it would go back to where it started from. Is that the?
Yes, but it never actually goes side.
Exactly. That's a very correct way of thinking about it.
But in the.
So what you are saying is that if you look at something that goes around here and then goes around here.
There was an ant on the thin part and it was walking to the fat part.
Yeah.
It won't go into the. It won't go into
That's
the glass.
Right.
But in the.
That's right.
Go both on this side and on the other side.
So this is an excellent question. Okay. So let me try to explain. Okay. So this is a very nice question. So what Drupad is asking is that, okay, so we had illustrated the two sides of a Mobius band by taking an ant crawling all around and then coming to the Mobius band and having the orientation reversed. Yes? And the question is, can I summarize your question? Does the same thing happen in this figure? It does not. Why? What's going wrong? Correct? Yes? Okay. And as he points out, the same thing does not happen here. Why is this? Because we have cheated in this picture. Yeah? So this handle is actually cutting the surface itself along this round guy. Yeah? So what's the difference between the Mobius band and this one? A Mobius band is faithfully embedded in 3 dimensions. Yeah? And this Klein bottle is not embedded in 3 dimensions. It's actually intersecting itself. So in order to make it faithfully embedded, you'll have to increase dimensions mentally by 1, and you'll have to put it in 4 dimensions. Yeah. I mean, this is not too hard. So for example, you think of a string, yeah, and you put the string and make it intersect itself in a flat 2-dimensional space. You can't wiggle it a little bit. Yeah, so locally, look at the x-axis and the y-axis. So the string has gone a huge long loop and has come back to where it started off, and locally it's the x-axis and the y-axis. You can't wiggle the string lying along the x-axis a little bit and the thing lying along the y-axis a little bit and hope that they'll become disjoint in 2 dimensions. What you can do is make a slight arch in 1 extra dimension. And then they are going to become disjoint. So what happens is that you look at this circle of intersection here. Imagine that there's an extra dimension. Allow yourself time, say a movie of circles. Yeah. So what happens is that this sequence of circles comes here, then it takes a jump in 1 dimension, then comes back again and joins that. Yeah. So then you're going to, basically you're increasing dimension by 1, and you're going to make this embedded. But in 1 extra dimension. But once you're in 4 dimensions, the notion of inside and outside does not make sense because it's already just a 2-dimensional gadget. Yeah? Yeah, so one has to live with it. Yeah.
Okay. Sorry, there's a question.
So my question is about the classification theorem that you spoke, that any closed and orientable service is homeomorphic to a sphere with n handles.
Yeah.
So I mean, every service is not obviously closed and orientable. So
That's right.
There are non-closed and non-orientable services.
So these are examples. The Klein bottle and the Klein bottle is an example of a closed non-orientable surface.
Yeah.
The Mobius band is an example of a non-closed non-orientable surface.
Yeah. So
yes?
how do you classify them? I mean,
Okay. All right. So for closed non-orientable surfaces, there's a similar classification theorem. Essentially, it says, I mean, there's a building block. What we were saying is that the sphere with a handle, right? A sphere was the simplest thing, and you were attaching handles to it, and that was doing your classification theorem. Here, this Klein bottle is built out of 2 of these building blocks. They're called projective planes or cross caps. Yeah? So essentially, a sphere with n cross caps is all closed non-orientable surfaces. These are names, but this is an example. Yeah? Now, when you go to the non-closed world theorem, they cannot be classified in that sense. There are pretty wild phenomena that happen.
So is it an open problem? Like you
No, it's not something anybody really bothers about because, so basically, just classifying it for the sake of classifying is not. So they would have to arise naturally. I mean, see, the thing is, these are objects of study. So it will have to come up naturally in some field of mathematics, and then you study them. Yeah? So just study, I mean, there are wild topological open non-closed surfaces which are of interest. Yeah? But just the world of all non-closed surfaces, yeah, is too wild for us to put a reasonable structure on them. So unless it has interaction with, typically in complex analysis, typically some other fields of geometry, they do arise, and then we do try to classify them.
Thanks.
Hello, sir.
Yeah.
Sir, this is more of a personal question. At what age did you get mad at mathematics, sir?
About.
I mean to say.
Mad at mathematics.
I mean to say, what inspired you to become a mathematician?
I don't know. I mean.
There's actually a related question from upstairs. What inspires you to study shapes?
Well, So I think here's the point. See, again, so there are, just as there are scientists and scientists, there are mathematicians and mathematicians. It's just that I am comfortable with a visual way of thinking about mathematics. And so one naturally gravitates towards shapes, yeah? So it's not something it's something that happens fairly naturally. If somebody is attracted towards numbers, one would be studying numbers. If one were interested in trying to find out fundamental laws that govern the physical world, one would be studying physics. So these are things that natural curiosities one has, and then one just follows them. That's it. It's not that you make a very serious, okay, from now on I'm going to study shapes. No, it doesn't happen that way. Yeah.
I'll just read a couple of more questions from upstairs before we come back. There's one question, I'm not very sure what exactly it means. Can different topological objects have different structural integrity? Is there a formula to calculate integrity based on topology? I don't know if you want to try to make
parse that question.
Yeah.
Oh, okay. So I think this was basically, I think I mentioned made some loose statements about defects in materials, and this is probably, so it's, I don't know enough about it. I mean, there are people here who know much more about it.
No, but maybe structural integrity in even in a sort of maybe just as being something structurally from structural rigidity. Because it says, is there a formula to calculate integrity based on topology? In some way, probably the formulas that you showed are formulas to capture the structural rigidity, right?
Yeah, that's right. That's right.
Formula.
Okay. So let me try to parse this question. So, for example, I mean, there is a field of mathematics and, with a lot of overlap with physics, which has to do with stability of systems. So I don't know whether this is answering the question, but it's answering a question. So, for example, I mean, if you move things a little bit, is it going to remain stable or not stable? So, for example, I mean, here if you deformation is some kind of disturbance to a topological structure. What remains invariant is this number. So that number is stable under local deformations. This gives rise to a certain part of mathematics called dynamical systems, in physics, chaos, etc., which basically allow us to quantify, not quite topology, but it has overlap with topology, quantify what kind of structures are stable under small deformations, what are not. So it's, I think one should look at the answer in this field of dynamical systems and chaos.
There was a question, this event is also being live streamed, so there was an online question, and so I wanted to just encourage that because it's the first of its kind. So this is from Sriram Agarwal, and he wanted to just maybe you can very briefly say what is the difference between homomorphic and homeomorphic.
Okay.
It's a little technical question, but you can just...
Okay. So typically, these are just words. So really, I mean, it's just a certain choice of words. Homomorphism is typically in the context of algebraic structures. Homeomorphism is in the context of continuous structures. So that's really the broad difference between them. So one is algebra, the other is topology or geometry.
So we'll just take a last couple of questions maybe here. I know there are still many, but we have to, it's nearly 6 o'clock, so maybe 2 questions here. The 2 people who raised their hands earlier.
Go ahead, Use the mic,
Is it on?
You can use that mic.
So I wanted to know what makes a client bottle closed and Mobius strip open.
Okay, that's easy enough to answer. So what happens is, so why is this Mobius band closed? So basically, it's if you start, it's not closed. So you take, imagine yourself situated here, imagine an ant, and it goes to this point, and then it falls off the Mobius band, right? So for example, a much simpler thing is just look at the surface of this guy, yeah? Right? So this is not a closed surface. So if one walks along here, just this square here, yeah? So if one reaches here, and if one tries to go further, one falls off the surface. Okay? So there is a well-defined boundary. Yeah? Having a well-defined boundary is what defines that boundary. Can be within, you can think of it either as within the Mobius band or as the boundary of the Mobius band. Yeah? So I think the difference is this flat earth which we used to think of and the round earth. The flat earth is something which is not closed. Yeah? The round earth is closed.
Last question.
If we consider a Mobius strip of width 1,
yeah,
and we cut it, we pick any number between 0 and 1 and we cut it along that width, then what will we get? For specifically, if we cut it along length half,
what
then we get
by cutting along length half?
Means if the width is 1,
yeah,
and we cut it along the midpoint of.
Okay, so basically you're saying you look at this middle circle that's there.
Yeah. If we cut it along it. If you cut along along half length, then we get two distinct rings.
No, you don't get two distinct rings.
Not distinct, they will be joined like a chain.
No.
I just want to know what will happen.
Do it once. So this is a good exercise. Go home and do this, and if you cut along it once, you're going to get a single connected object.
And what will happen if we cut it along any width between?
Try it out.
Okay, so
it's a very good exercise. Try it out. Yeah.
I think we have to cut things short. Mahan is around. You can satiate your curiosity over coffee, rather. But before you leave, I just wanted to announce there's another copy with curiosity very soon after the 10th December on a very different topic, paleovirology. You can see the poster outside. So please come for that. Ask your friends to come as well. And remember, there's the public lecture by Kip Thorne in ICTS campus on 11th January. There'll be also a public lecture and panel discussion in Christ University on January 7th on the usefulness of useless knowledge like topology. So please come for that as well.
Yeah.
Thank you.
Yes, super.